Hello. Purpose of this video is to cover the assumption testing protocols that you can use when doing analysis of variance. You will recall there are three main assumptions for the ANOVA test, which is that the variances across different groups are supposed to be the same, the homogeneity variance assumption, that the residuals from the model should be normally distributed. That's often mistakenly understood to mean that the data should be normally distributed, but that's not exactly the same thing, and that the observations across and within the group should be independent. What I'm going to demonstrate here is the Levines test for the homogeneity of variance. Levene's test is one of the non-default options that can be generated with the SPSS ANOVA protocol. And I'm going to demonstrate that now using the physics data set that we had from class. Again, this is a simulated data set where the group indicates the section that the students were located in. Exam is their score on the first exam in this physics class. And in this case, because of the analysis, we needed to introduce a third variable, which was the order in which the exams were actually graded. And that's a number indicated here. So for example, the first student in this group this person's exam was graded 44th in order. The analysis that we're going to run first is under Analyze, Compare Means, One-Way ANOVA. We'll move Exam to the dependent list. Group is the factor variable. And under Options, I'm going to ask it to generate the homogeneity of variance test, a test that's not turned on initially. I click Continue and OK. And the output gives me not just the ANOVA summary table, which has the significance that we were familiar with from before, but it also generates the homogeneity of variance test, or Levene's test. In this case, the score is 1.207, and the probability of seeing this by chance is 0.313. Now, it's important to remember here, the null hypothesis is that the groups have the same variance. So in this case, we want to fail to reject the null, and this p-value would give us that result. The next was the normality of residuals. To confirm this, we'll use the Shapiro-Wilk test. Unfortunately, this is not easily generated or obtained using SPSS. First, what we need to do is run the model where we actually generate the residuals. Under Analyze, I'm going to use the general linear model feature with the univariate result. I'll put exam in the dependent variable, group in the fixed factor variable, and for this I need to save the unstandardized residuals. To clarify what's actually happening here, I'm also going to save the predicted values so we can see what's happening. I click Continue and OK. I get a result similar to what I would expect for the ANOVA. When I look at the data, I see that in group 1, all of the values have the same predicted value, 74.13. That's the mean for that group. The residual in this case is the difference of the observed score, 91, from the predicted score, 74.13, the group mean. And in this case, this individual was 16.87 points above the predicted value, which was the group mean. So what we've done is we've obtained the average for every person in their corresponding groups and how far that person was away from their average. Now with this information using the residual, I can actually do the Shapiro-Wilk test. Under Analyze, Descriptive Statistics, Explore, I'm going to ask it to look at the residuals for the exam. And in this case, for the plots, I'm going to ask it to run normality plots with tests, and this will run the tests that I want to see. I click OK, and as usual, I get the standard information, this descriptive statistics for the data set. But in this case, I also get a test for normality. In the test for normality, in this case, I'll use the Shapiro-Wilk test, and I notice that my statistic, 0.965, has a 0.007 probability of occurring by chance. Now to clarify, the null hypothesis in this case is that the data comes from a normally distributed distribution. So with a p-value less than alpha, I would actually reject that claim. As it turns out, my data appears to have something of a bimodal distribution, and this can be seen in a few of the plots. This inverted S shape is one of the indicators that we have a bimodal distribution. So it's not surprising that we actually obtained a result that indicated that we would reject this assumption. However, what we'll find out is, in the grand scheme of things, this assumption is probably the least pressing of our concerns. The next assumption is the independence of observations. This analysis is not easily done, and one approach is to use the Durbin Watson test. Now again, this requires that we know when each measurement was taken, and even then the conclusion that we're going to obtain is iffy at best. So in this case, again, we code the data with two variables, the scalar variable, which is the score that we're going to analyze, and the temporal variable, which probably is an ordinal variable, which indicates the order that the data was collected. The Durbin Watson test assesses if there's any type of relationship between the errors as we're predicting over time. The hope is that there is no autoregressive correlation, meaning that the errors from one term appear to be related to the errors of successive terms as we're taking data over time. If our p-value is less than the significance level, there are serious concerns, but the truth is, even when p is greater than alpha, there's actually not a lot gained from this particular test. Worse, SPSS does not actually give a p-value for the Durbin Watson test statistic. Instead, it gives the Durbin Watson statistic, and we're asked to compare that to an interval of 1.5 to 2.5, where if it falls outside that interval, we would be inclined to reject the null hypothesis, which indicates that there would be an autocorrelation between the errors, which is not desired. If we end in this range, then we interpret this as evidence for lack of dependence, or in this case, the hope is that proof of independence, but that's actually not possible. Now, to obtain this, we need to go to Analyze, Regression, Linear Model. We'll put the exam score in the dependent variable and the order variable in the independent variable. Under Statistics, we'll ask it to generate the Durbin Watson statistic. We'll click Continue and OK. And in the model summary information, we're given that the model has a Durbin Watson score of 1.855, and this falls within the acceptable range of 1.5 and 2.5. So we can relatively reasonably assume that there is no autoregressive correlation. So in this demonstration, what we've seen is that the model assumptions were okay for 2. We saw that there was homogeneity variance, and generally speaking, we don't have evidence that there was lack of independence in the observations. We also saw that the normality assumption for the residuals may not have been satisfied, but again, in the assumption testing protocol, that's actually the least of our concerns. I hope this information has been useful. Thank you very much for listening.